Hello everybody, welcome back to today's session on transformer encoder. In this video, apart from building the encoder layer by layer, we'll be also discussing what is layer normalization and what is batch normalization, the difference between these two, right? Okay, so let's start from building one of the sub-layer of transformer encoder. We had learned positional encoding, then that positional encoded data or the sequences were fed into the multi-head attention. That was the previous session, and then from the multi-head attention the outputs are going into a add and norm layer. There are two parts to this. One is the add and then second is the norm or normalization. What is add doing? Add is basically taking input from the sub-layer, which is the multi-head attention output. It is taking that input as well as it is taking the direct input from the positional embedded data that is also going directly to the add and norm layer, bypassing the multi-head attention. Now you will remember from our past video, if you don't remember, go back to the LSTM. Yeah, we had a video called attention visualization using LSTM. If you go there, you will see that we had similar kind of architecture where sequence length is large, where the depth of the network is also large, then it has a tendency to do gradient vanishing. Okay, so to retain the information so that it don't get lost when the network becomes deep, in LSTM we had implemented a gating mechanism, which is basically directly feed the input to the subsequent layer and a gate mechanism will control it. So this is what we are seeing here, that the bypassing the multi-head, there is one skip connection which has been given. This architecture also is prevalent for a very deep CNN where images are processed to retain useful information from the previous layer. So why do we do such thing? It is to skip connection, which is flexibility in learning, where the sub-layers beneficial informations are retained, encourage feature reuse, all the same thing, basically preserve information from the previous layer, and the gating mechanism decides which one or how much information to retain and how much information to discard, allowing the network to be very deep. That's what we are saying. For deep network, it is the training. Now that's about the skip connection or the add part of the add and norm layer. Now we are going to the normalization layer. Now before we go to the normalization layer, we want to touch upon certain basics, because normalization terms are used in various contexts. Throughout our journey, you might have faced this terminology in various contexts. So let's just consolidate all the places where we have utilized the normalization term. So the normalization first was used in our first video, which was the dot product, where we were learning about vector, and we learned that in the vector there is something called normalizing the vector, which is nothing but dividing the vector by its magnitude, and thereby we get the vector norm, which is the magnitude is calculated like this, vector, the norm is calculated like this, and once you try to get a unit vector, it is nothing but a normalization of the vector. Okay, following that we have subsequently faced softmax function. When we have first discussed about the additive attention or Badnav attention, there we had a block called how you are converting the output from the neural network. All the vector values were converted into a probabilities, and then subsequently in all videos we are actually using softmax layer. This is very frequent. There also we are doing normalization. What exactly we are doing? We are actually converting the values of all the vector components within 0 and 1 so that they represent a probability or a weight. Converting or scaling the values, scaling the data points within 0 and 1 is actually normalization. Although they are used in different contexts, for example softmax, the idea is more or less same. In the softmax we said that basically you are taking a value, exponentiated it, and then adding all other values as a denominator, therefore you are converting it as a weight. Now let's go back to what we are discussing for this purpose, is a standard pre-processing step where we want to scale the data. One data in the range of, let's say if we are talking about distance, then one represented in kilometer, another represented centimeter, it becomes very difficult for gradient descent to identify the minima. So therefore, all the data are scaled in a particular range, and there are two ways we do it. And this was very well explained through this visualization in this blog's post, Johnny's machine learning blog. You see this green color was representing the original data, and you can either do a standardization, which is basically finding the mean and spread the data or scale the data such that the 0 becomes the mean, and spread of the data, the standard deviation of the data, is between 1 and -1. So this red color is representing the standardization. Then you have the blue patch, which is normalization. It is the technique which is called the min-max technique. You see the formula how it is done. You find out again the minimum value, and then you do this kind of subtraction in the numerator and denominator, and thereby you bring the data between 0 and 1. The range becomes this. Essentially, you are rescaling the data from, you see, this is going up to 6, the scale. However, when you rescale the data, either through the standardization, we have made it from -1 to 1. Mostly the data density is here, and there are certain outliers which is going beyond the standard deviation. While if you are trying to rescale them between 0 and 1, which is called the normalization, it is the blue patch. Okay. Now, when you go to our case, which is how do you apply this for normalization within the neural network, you again have two sort of stuff. One is the batch normalization, another is the layered normalization. So in the batch normalization, what you try to do is that in the batch you have several data examples, right? Now let's say there are 5 such examples, which is represented by M. So along this rows, or rather, yes, along this line, which is, you can consider this as a column, x11 to xm1. If this is a column, your mean is we are trying to find it within this column. So the formula which is used for the normalization is much like a standardization formula, although they are using normalization, and that is the reason we are refreshing our memory about this terminology, otherwise it becomes confusing. So it is basically standardization formula where you are trying to spread the data, keeping 0 as the mean, and then both sides of the mean you are trying to spread the data. So this is more of a standardization. However, we are calling it here as the normalization. Okay, now you see this is the formula. So your first task will be to find out the mean, mu, right, and the standard deviation. So to find out the mu, you are, by the way, you have some epsilon term here. This is the formula used in the TensorFlow Keras library. So not to bother, but you just see that this is a learnable parameter here. Now focus here in the mu. The mu is calculated by 1 by m, right? M is the number of examples in the batch, and then you do the standard deviation calculation using this formula. Let's say this yellow line where it has reached up to 2, or this blue line which has gone up to 4. You see now the blue line or the yellow line, both of them are rescaled within somewhere in the -1.7 to 1.7. That's the maximum range. So this has been squeezed, the scale has been changed, and that's how each of the data has been rescaled. However, the reference for the rescaling is all other data points in the batch. As opposed to that, when you come to layer normalization, in the layer normalization you are not looking at the examples in the batch. What you are looking at is the one single example. Within that you are taking all the values, and that is used to rescale, which means if it is 5, you can say -15 to 5 is the data spread, whereas when you rescale them using the same data points, if you are following the formula what we have just given here, which is these are the datas x1 to xdm, which is the embedding dimension, then it is the mean is found across all this data. you got the difference from the batch, right? Batch normalization. Then standard deviation is calculated. Then similar formula is applied. Only how the mu was found is the difference here. And it is very well represented here. If this is the original data, your rescale data is now like this. Yeah, the shape remains almost same, only the scale got changed. Fair enough. Now moving forward, you are going to another visualization, which is if this is the data and these are your rows, you see these are your rows, then within the row, using all this value, for example 0 0.0, 7.8, 9.7, these are the value which will be used to calculate the mean, and then apply that formula x minus mu divided by the standard deviation to find the layer normalization. Whereas when you are trying to do the batch normalization, you are taking each of this column. And if you do the plotting side by side, we can see if this is the original data, let's say this blue curve, you can see that the blue curve is actually, the shape remains same here. See, shape remains almost same even here in the batch normalization. Only thing which has happened is that the batch normalization has done it with reference to all other data. That's why you can see there is some sort of symmetry amongst all the examples, right? Whereas when you're coming to layer normalization, it has been rescaled but independently from other data points. Another visualization once again, basically if these are our sign encoded data of various scales, they are all rescaled within this, but that's not equivalent to the batch normalization. Fine. Now why batch normalization? When do you use it? Batch normalization is done when you are trying to speed up the training by increasing the batch size. There's a lot of data, let's say normally the batch size will be 16, 32, 64, but you can increase it as high as 2000 or 4000 one batch at a time. When they go to GPU, the speed of processing becomes very fast. When you are increasing the batch size, if you do the normalization at the batch layer, it serves a good purpose, okay? And it actually works as a regularization term to control the overfit. When you are doing image processing, you can understand many images will be similar. Maybe they will be varying by intensity somewhere, maybe varying by colors, and you are trying to do a classification. So you give many similar example of some sort to instruct that this is your class, right? In that cases, when within one example, with the other example, there is certain similarity, there is some dissimilarity as well. And then if you do a normalization amongst those data, it serves a great purpose. So batch normalization work well in those cases. On the other hand, it is dependent on batch size. So when the batch is actually low, empirically it is found that it will degrade the training, right? And when you are going for a sequence network, when the feature is not kind of spatial alone, but the feature has a temporal nature, where you have the basically you have many sequences within one feature, right? Many words. One word going to very high scale, another is lower. If the values are so high and low, you want to normalize within that. And then instead of that, if you compare it with other sequence, other sentence, which is maybe having a completely different sort of sequence, then the batch normalization doesn't work well there. So therefore, when you are coming to the layered normalization, it is good when you apply it on the sequence dependent data. And then of course it is independent from the batch. Therefore, whether the batch is low, high or small, the number of batches, this will always give you a normalization benefit. Now that's it. That's just a refresher before we apply the normalization here. Coming back to this transformer encoder construction, what we are observing here, that after multi-head a add norm is layer is given, then it goes to a feed forward network, and then again a add norm is applied. This is what we can say is a encoder layer. And then when you stack up several such layers, in the paper it was 6 number of layer, n into, and several such layer will be there inside a encoder. So that will constitute the complete encoder. Basically within encoder you have sub layers of encoder layers. Within the encoder layer you have all this different layer, right, which is positional encoding, multi-head attention, going through add norm, going to feed forward, then again going to add norm, finally giving you the sub layers output that will go to another such similar encoder layer. 6 of them will be stacked together, and therefore the final output will come from the encoder. Let's go to the code now. Okay, we are now trying to build the add norm. See what is going on here. So in the add norm, you are utilizing this layer, keras layer normalization. That is what, if you just feed into the data, will do the normalization. In fact, all those the plot which I have shown you, like this plot, this data, the original data was actually passed into a layer normalization. You see, we have done a normalization, layer normalization, batch normalization using this. So these two keras module will be able to give you the normalization automatically. You are in the add norm. So coming back here, we are just utilizing this layer normalization here. In the call method, which means whenever you are giving the data, you are giving two data, right? And the add norm, just the way we displayed in our PPT, you can observe here that we are basically giving the two input, one from multi-head and another from the previous input. You see, this is the input, which is nothing but the X input. This is where you have the input and the multi-head attention input. These are the two things which is happening. And then finally, you, going as an input, adding them together, and then passing this to the normalization process, which is the norm. So it is exactly the same thing what we displayed in the PPT. We are just coding it on the same line. So add norm is done. We are now moving to the position wise feed forward network. Feed forward network, as you can see, we are using two number of dense layer, then and a dropout layer. That's it. So basically you are giving the input which is coming from the add norm, going to one dense, do a dropout here. Dropout is required because you are building 6 number of layers stacking up together. So therefore you need a regularization, otherwise it will overfit. And then dropout is applied only when you have the training. When it is inference, then at that time the training is false. So you don't do the dropout that moment. And that's it. It's pretty simple. Let's move to the encoder layer. You see, encoder layer, we are using two types of multi-head attention. One which we have built, if you remember, otherwise you go back to our multi-head attention video and see that we had described there one implementation which is our own, which we are naming it as a BBMHA, and the other one is the keras library multi-head attention. Both are there. If you just set it to true, it will be using our own implementation. So that is how during the final training we'll have both versions. And then you have the add norm which you have just built in this video, feed forward network, and all of them are nothing but the parameter. Going to the call method, you can see that you are telling that, so basically how many number of heads etc. getting passed to the multi-head attention. Then you are calling the multi-head attention here. The output of the multi-head attention is going to the norm, and inside the norm you are also passing in the raw data, the position embedding data, and finally you are passing it through the feed forward network, again doing the normalization, add and normalization, returning the output. Quite simple, exactly the same step which you have followed in the PPT. And then 6 number of such layer has to be stacked together to build the encoder, right? So coming here, you say how many number of layers, that's a parameter, and positional encoding, because in the encoder you will give the raw data. Inside the encoder we will do the positional encoding, and then this is what we will be passing it through a loop to construct the n number of layers. In our code you are saying that the first layer we are building outside of the loop with debug is equal to true information, and second is forcefully debug is false. Just to do some kind of printing for testing, I have isolated the first layer from this loop. Otherwise it is basically, you see how many number of layers are there, and then just iterate through them to build so many number of encoder layers, stack them together to build the, you know, the encoder. In the encoder, again, exactly if you see the PPT, we do the same thing, which is positional encoding is there, then it is passing through the encoder layer using the loop. Encoder layer automatically takes care of the add and norm layer and the feed forward layer, and finally it is returning the X. It also collect the weight if at all you need. Normally from the encoder we don't want to get the weight, okay, in a transformer encoder decoder architecture. So that's how you have completed our encoder coding. Now if you go to the testing part of it, you do the encoder layer testing. Very simple. Encoder layer will take embedded data, so we have passed in embedded data here, and then the output is this, right? And then just by turning the switch off, whether you want to use the custom MHA or you want to in the default layer, the Keras MHA, the multi-head attention, you can see that they are actually working, right? Here you've got the attention weight and all of that. Transformer encoder, again testing here. You do the transformer encoding and test all the switches are working. This is the Keras layer. This is our own implementation of multi-head, and therefore it is printing out all the debug information. This has been already explained in our multi-head attention, so I am not going through all this. The only thing we will notice, that is the output correct. Yes, the output is correct, because we remember that the encoder output will be the batch number. We have taken two data instance here, the sequence and the D model as the dimension, which is the 512 we have set. That's how the D model will come in here. So we have completed our encoder, transformer encoder construction layer by layer. We started with the concept, then also completed the code. One small thing to be noted, on which we will have a elaborate discussion later, that this encoder, whatever we have built, that itself can be used standalone to address many tasks. So transformer is such that you can either use the entire encoder decoder as a, you know, machine translation. Also there are many tasks where encoder itself performs very well, and so is the decoder as a standalone. Okay, so that is at a later video. As of now, stay tuned to look forward to the next video, where we will be building the transformer decoder and the training the complete encoder decoder. Stay tuned, we are coming back soon.